then I know that we are ready for those scenarios, the complicated ones. With the complicated ones are not just based on circular motion, they are based on circular motion and advanced mechanics. So, circular motion, you weakness the whole thing just collapses. So we first have to make sure we understand circular motion. So this is a good question to check if you understand or not. So can you guys try and see what the answer is? I mean, if you guys get some answer, just share with me. Let me see. So কি বলছে এখানে একটা horizontal plate আছে free to rotate about the vertical axis. So যেভাবে a small mass m is placed on the plate and distance d দেওয়া এখানে, and আমরা কি করতেছি, আমরা স্পিডটা gradually বাড়াচ্ছি. So we need to figure out what is the maximum number of revolutions per minute that we can apply before a massটা উড়ে চলে যায়. So yeah, there is a point where the mass will just fly off, right? If you spin too fast, what is that rate of revolutions per minute? All right, so 4 of you gave me answers, 5 of you, 6 of you. So I'm really glad everyone is correct. Very good. Okay, so Anha, Ishraq, Naumita, Sadat, Naila, Nanjiba. Very good. Okay, so yeah, I mean, at least 6 of you are ready for circular motion. Bakira share core answers. Dekhi. We'll give a couple of minutes. What do you think is the answer? Karon eta jodi paro, we both will be confident moving forward. Okay, so it's not just you, it's also me that I'll be sure যে আচ্ছা না তোমরা একটু বুঝো জিনিসটা. Let's move ahead. So একটু try করে দেখো কি আসে answer. All right, so start query process-টা বাকিরা যারা answer করো এখনো তোমরা answer পেলে share করো so that I know what you guys get. So what is actually happening here? Circular motion, right? Circular motion is happening here. Now this object is going to go in a circle around this surface, right? But something has to provide a force towards the center to keep it circle. So there must be a force acting towards the center. Now, ওরা বলে দিচ্ছে that's frictional. Frictional force is that force that keeps this towards the center, right? So there's frictional force available here. That's what we know. So, circular motion is possible because frictional force is available. That's the, bottom line here. Kintu, what we need to know is as your object starts to go faster and faster, listen to this carefully, okay? As your object starts to go faster and faster, we have seen that F equals to mv square by r, right? So as the object goes faster and faster, more and more centripetal force is needed, okay? More and more centripetal force is needed. Right, Fairuz, you're correct as well. So more and more centripetal force is needed. Now, can this system provide me that new excess centripetal force? Check korte hobe. So we need to do our math and figure out এখানে যে ফ্রিকশনটা available এটা কত ফাস্ট রোটেট করতে allow করে, কারণ ফ্রিকশনটা হচ্ছে লিমিটেড. Okay, ফ্রিকশনটা লিমিটেড. Omio, you're right as well. Very good. So এখন কেমনে করব এটা? How do we solve this? So আমি এখানে start করি কোয়েশ্চনটা 5 মার্কস এর জন্য কি করতে হবে. So first of all, we need to find out how much friction is available. Okay, so first or দেখো explain your working বলছে. So when they say explain your working, you need to have some statements here trying to explain কেন কিছু করবা তুমি, মানে whatever you're doing, why are you doing that? So one of the statements we write down is the frictional force is equal to the centripetal force, because that's the force acting towards the center, right? So the frictional force is equal to the centripetal force. First, you explain that. Then what we do is we find out the frictional force. So how much is friction? চাইলে লিখতে পারো maximum, because এর তো বেশি friction হচ্ছে না. So they have given us the formula. Friction is 0.72 W. So 0.72, it says W. W is weight, right? Because M is mass, but we do not know mass though. So I'm just going to write here mg. Okay, so that's the friction that we have. We do not know the value of mass, so let's just keep it like that. Then what do? Then we write down 0.72 mg is equal to the centripetal force, right? So centripetal force হচ্ছে mv square by r, that's a possibility, or m omega square r, right? There are two formulas for centripetal force. What are they? mv square by r or m omega square r. The thing is that which one do we go for? So we'll go for this one this time around. I'll tell you my reasoning behind it. We are trying to find out revolutions per minute. So it's to do with time period, right? যেটা এখান থেকে আমরা বের করতে পারবো, এখানে আমরা এটা পাচ্ছি না. Now, is it going to be wrong though if I use this equation? Absolutely not. You will still get a V, and then you can find out what you need. But why not just use a formula that is dedicated for this purpose, right? So এটা দেখি. Tanim, your answer is close, but at a different হওয়ার কথা. Something's missing. Do you take GS10 or something? 9.81 নিয়ে করতে হয়. আচ্ছা, anyways, আমি সলভ করতেছি, তারপর দেখো ম্যাচ করে নাকি. So my centripetal force is equal to m omega square r. R is how much? 35 centimeters. So 35 divided by 100. So you can see conveniently mass cancels out, and you'll see this very often in circular motion. Circular motion আমরা একটা জিনিস নোটিস করি, that mass প্রায় cancel out হয়ে যায়. Mass অনেক জায়গায় cancel out হয়ে যায়. What does that tell us? Tells us that circular motion mass is independent. মানে তুমি বড় mass রাখো ছোট mass রাখো, অনেক সময় দেখা যায় mass এর কোনো effect থাকে না. So anyways, that's something for later on. I'm just letting you guys know to keep that in mind. The mass cancels out a lot in circular motion equations. Anyways, that's not the concern right now. So we're going to find our omega here. So omega is 0.72 into 100 divided by 35. There's a 9.81 as well. Root over. So can you check what's the value of omega? Omega is not the answer. It is our way to the answer. So omega কত আসে? $4.492. Okay, 4.492 is our omega. আচ্ছা, এখন কোয়েশ্চেনটা হচ্ছে, what are we trying to find out? We're trying to find out number of revolutions per minute, RPM, revs per minute, right? So এটা কেমনে বের করতে পারি? So what I'm going to do is I'll break down omega. Omega equals to 2 pi by t, which is 4.492. So এখান থেকে আমরা টাইম পিরিয়ডটা বের করতে পারবো. So we can use this to find out what's the time period of my oscillation. Can you help me with that? 1.4 বাকি যেরকম আসে, 1.39. Okay, 1.399. That's the time period. Acha, now what do? Now we can do a lot of things. You can use frequency formula, you can use unitary method, you can use the 2 pi f formula অনেকে যেটা use করতে চায়. So a point থেকে going forward, it's your choice what you want to do. I personally like unitary method. কেন আমি বলি, they want me to find out the number of revolutions per minute, right? See how I write my unitary method. If one revolution takes 1.4 seconds, time period is the time for one revolution, right? One revolution takes 1.4 seconds. Then how many revolutions will be completed in 60 seconds? Why 60? Because they want for a minute, right? So I'll do my math here, and my math will reveal to me the answer. So x hoche 60 divided by 1.4, which is 42.9, I think, revolutions per minute. So what do you write your answer as? 42.9 is fine. 43 is better. Let me explain why. So 43 হচ্ছে better. কেন? বিকজ হচ্ছে যে রুলটা হচ্ছে ফলো করা হয় এ লেভেলসে, রাইট? তোমরা জানো অলরেডি এ দেখে আসছো, A2 তে এটা একটু বেশি অ্যাপ্লাই করা হয়। is the significant figures of the data is usually kept same for your final answer. So two significant, so we keep it to two significant there. Okay, but 42.9 is not wrong though. They will accept that as an answer as well. So don't worry about that. Okay. Acha, there's a follow-up question here. The follow-up question is what? The plate in B is covered with, when stationary, with mud. It's like, pottery wheel or not. So your pottery wheel, so there's mud on it, right? So there's like mud here. So they're asking you that suggest and explain whether the mud at the edge or the center will first leave the plate as the angular speed is slowly increased. So as you start increasing the speed, where will you notice the mud fly off first? The edge or the center? What do you guys think? Quite easy. I think now you should know by now what the answer is. কোথায় তুমি যদি একটা প্লেটকে স্পিন করতে থাকো, এই যে প্লেটকে স্পিন করতে থাকো at very high speed, right? Where will you notice the mud fly off first? এই প্লেটটাকে খুব তাড়াতাড়ি স্পিন করতেছো, দেখবা যে জিনিস উড়ে যাচ্ছে প্লেট থেকে, রাইট? সো কোথা থেকে জিনিসগুলো উড়ে যাচ্ছে? সেন্টার থেকে উড়ে যাচ্ছে নাকি ইউল নোটিস দেম ফ্লাই আউট ফ্রম দি এজ? The edge, right? Exactly, the edge. Now why? So first আমরা লিখবো suggestion, the edge. Now why is it like that? So let's give it a mathematical approach. So we know that centripetal force is equal to m omega square r, right? That's the centripetal force. So for the objects that are very far from the center, the centripetal force needed is supposed to be very high, right? মানে যেগুলো যত দূরে থাকে ওদের বেশি centripetal force লাগে, and the closer you're towards the center, the less centripetal force you need. So the question is, where is it more likely that the particles will not have enough centripetal force available because of friction? At the edge, right? Because edge is further away. So how do you write this answer? So you say that the particles at the edge will leave the plate since they require the highest centripetal force, which the plate might not be able to provide, which the plate might not be able to provide because friction is limited, right? So জিনিসটা কি, মানে what's the point I'm trying to make here? So look at this. This is the circle, top view. Okay, and let's say this is the center here, and there are chunks of mud here, chunks of mud at different distances. So distance গুলো আমরা একটু লিখি. So let's say this is D, 2D, 3D, 4D, 5D, এরকম করে distance গুলো, right? And what is acting on each of them? Towards the center, there's friction acting on each of them, which is the same amount of friction. Okay, so let's say the friction is 50 Newton fixed. Okay, just an example. If this is rotating at some speed, let's say 20 meter per second, this one will only need, right? This one will only need 5 Newton to stick to the plate. This one will need 10 Newton. This one might need 25 Newton. This one might need 40 Newton. This one needs 55 Newton because F equals to M omega square R. If you do the math, it is a constant because mass same, omega same. The further you are, the more centripetal force you need. So we can notice that the further we're going here, the amount of force needed to keep in circle is getting larger and larger. I need more and more, right? So this needs 5 Newton. 50 is available. Perfect. It will go in circle. This needs 10 to be in circle. 50 is available. No problem. 25, 50 is available. No problem. 40, 50 is available. No problem. But this piece of mass needs 50 newtons, 55 newtons to stay in circle. But you can only provide 50 using friction, right? So 5 is missing. So there's no way that this mass can sustain its circular motion. So what is this mass going to do? It'll just go off the circle. Okay. Yeah, the friction is same for each of them because we're using same mass, right? And if we are using same mass, the formula is F equals to 0.72 W. I'm using the same idea. So if the mass is same, the friction is going to be same for all of them. There's a question, can we refer to F equals to mv squared by R? Too risky. Let me tell you why. F equals to mv squared by RA. I told you that radius barle centripetal force মনে হবে কম লাগে. Remember, I think I discussed this. So then you might have the opposite answer. Why? You might be thinking, oh, তাহলে দূরে গেলে তো কম force দরকার. তাহলে তো problem না. But why is this equation not good for relationship analysis between force and radius? Is because the further you go from the center, the speed also increases exponentially. So you actually need more centripetal force. So this equation can be deceiving for you when you're trying to analyze relationships of friction and forces. Okay, so try to avoid this. Always, whenever you want to find a relationship subjective for a question, this is the best equation to go for obvious reasons. Why? This is a constant wherever you are. এখানে সব জায়গায় omega constant, mass constant. So you know the radius and the force can be easily compared, right? Can we refer to tangential speed? Acha, here is the thing. To clarify করি এটা হচ্ছে সবাই কোয়েশ্চনটা করে যে can we say that the particle at the edge is the fastest? That's why it flies off. The particle at the edge is the fastest. That's why it flies off. The correct answer, the truth is, not really. Let me explain. The reason why it's flying off, it's not because it's very fast. The reason why it's flying off is because you cannot provide enough centripetal force to keep it in the circle. Take us, for example. We are now traveling at 1400 meters per second around the Earth, right? At a moment, we are traveling around the Earth at 1400 meters per second. Why aren't we flying off? Because the centripetal force that's acting on us is capable of keeping us in circle. So, you know, the value of the speed, the value of the tangential velocity is actually not the deciding factor. The deciding factor is, are you providing the right amount of force or not? Because here's the deal. If this thing was made up of a polished, ekdom perfectly flat at surface with very little friction, even at 2 meters per second, things will fly off. Even at 0.1 meter per second, things might fly off if there's not enough friction available. So if you look at the reasoning, at the end of the day, it's actually not the speed that's the problem. The limiting factor, as it should be, is the centripetal force. Is it available or not? If centripetal force is available, let's say this is made up of sand or something, right? Like, you know, the surface is very rough. You could spin it at 200 meters per second and things will not fly off. Okay, so yeah, the point is that centripetal force is the deciding factor. If you have the right amount of centripetal force, any circular motion is available. If you do not have this, even 0.1 meter per second, then things will fly off. Okay, so that's the reason why water on a surface flies off very easily, right? At the surface of water থাকলে উড়ে যায় খুব easily because the water friction খুব কম থাকে. So you get the point, right? All right, so আমরা আরো কিছু কোয়েশ্চেন করব পরে. বাট এখন একটু আগাই, আমরা টপিকটা নিয়ে সামনে যাওয়া দরকার। So today we will learn about this very interesting concept of circular motion called the conical pendulum. Okay, conical pendulum. So what is the conical pendulum? Let me first explain that, then we will try to figure out how does it do its motion. Okay, so let me show you a conical pendulum. So I think you guys know what a simple pendulum is, right? Simple pendulum is something that just goes back and forth. This is a simple pendulum there, right? So it's one dimensional, two dimensional to be exact, like, just going along a single plane, সামনে পিছে যাচ্ছে, কোনো 3D movement নাই, there's no movement along the z axis. Okay, it's just x and y axis of movement হচ্ছে. However, if we do certain things to it, right, like this, I think this, yeah. So what happens here is just a moment. There. Do you see this thing going in a circle? So it's 3 dimension, okay? তোমরা যদি না বুঝে থাকো, এটা কিন্তু 3 dimension যাচ্ছে। এই যে top view, sorry, side view এটা. So it is going around in a circle, right? So it's going around in a circle. Do you see the dotted line that represents the circle? But it is a pendulum though, right? Because pendulum definition key, it's basically a string hung from a fixed point undergoing oscillation. Is this a string hung from a fixed point? Yes. Is this undergoing oscillation? Yes. So it's a pendulum, right? But then how is it different from the other pendulum that we saw? This one is undergoing a movement that looks like a cone. Do you see? It looks like a cone with the triangle and everything. So that's why this is called a conical pendulum. And it is undergoing circular motion. At the bottom, there's circular motion going on. However, if I show you the forces acting on the system, right? These are the forces acting on the system. We see something strange happening here, which is there's tension acting in the rope, right? Tension act করতেছে কিন্তু. Do you see the tension? Blue. So that's acting on the rope. And there's your weight acting here, which is mg, which is acting downwards. But there is no force acting towards the center of the circle. Where is the center of the circle? Center of the circle is a flat center there. I'll show you in a diagram later on. But there's no force acting towards the center of the circle. There's a force acting towards the top of the rope. There's a force acting downwards, but there's no force acting towards the center of the circle as of now. So we need to figure out who's helping this object undergo circular motion. How is it even achieving circular motion? So that's what we're going to learn today, okay? So how do we approach right, Bihanga, you're actually correct. That's what's happening. So let me draw the diagram and explain. So what's actually happening? So let's first try to learn some of the terms that we'll be using for a conical pendulum. So first of all, there's the axis of rotation, this line. Then we have what else? We have the rope that will be spinning in a circle like this. The rope will be going in a circle, and at the end of the rope there'll be a mass here, and the rope along with the mass will go in a circle that produces that circle. Okay, so this is the path of the circular motion there. Okay, so this object will go in a circle like that. Now let's label some of the forces and label some of the things that we know and the things that will be provided to us in the exam. So exam আমাদেরকে এই অ্যাঙ্গেলটা প্রোভাইড করে দিবে, এই অ্যাঙ্গেলটা বলে দিবে. This is called theta. Okay, just a second. Right, so this angle is theta. This is the angle of like how much is this been bent. Okay, on এটা এদিকেও যেতে পারে, এদিকেও যেতে পারে, which will make a difference. So we'll look into that. And the other information that will be provided is the length of this rope here. Do you see the rope? The length of the rope. And the last information that they'll provide us is the mass of this object here that's spinning. So using these information, the angle, the length, and the mass, we need to figure out how is this undergoing circular motion. Now, let's try to first draw a free body force diagram of this mass, okay? So this is the mass. What are the forces acting on the mass? Let's see if that reveals to us something that we can use. So this is the mass. Just a second. Mass M. What are the forces acting on this mass? The free body force diagram. So there's one force acting this way, right? The force acting that way. What is that? The tension, right? The rope has tension, so tension is acting that way. So there. And there is another force acting downwards like this. There's another force acting downwards like this. What is that force? The weight, right? So this is your mg. From initial looks, right, you wouldn't see any force acting towards the center. Now, what do I mean by towards the center? I've been saying this for some time now, right? I'm talking about this force, AJ, the force towards the center of the circle, because you have to understand, this is the circle. This is the center of the circle. Students will think like, but tension to edike act korteche. Why is not that not helping circular motion? Yeah, that will make your object go in a circle like this, which is not the case. To me, tomar mathar upor diye gol kore ghurao like a fan blade or like a clock. Yes, tension is the answer. We don't need anything else. But not in this scenario. In this scenario, this is the circle and this is the center. So how do we find the force acting that way? So you probably have some idea about mechanics by now, right? So you can figure out what might be this force. So what do you guys think? One of you already answered correctly. Anyone? What do you think is that force acting towards the center? What could it be? Exactly. It is the horizontal component of tension. Very good. It is the horizontal component of tension. Tension has two components here, horizontal and vertical, right? So let's see. By the way, if this is theta, আমি যদি এখানে একটা reference line draw করি, এটা কিন্তু theta, right? So I hope you understand that. So I'll not keep that here. I'll draw it here. So this is also theta. So that means this is going to be t sine theta. Does that make sense? Horizontal component, right? And this is the adjacent angle with the theta. So what should that be? T cos theta, right? So this is the free body force diagram and the component breakdown that we have so far. But then what? What do we do with this? So there are two interesting points we need to address. Number one is this. Look at this. Eta circular motion korteche na? See the side view. If you look from the side, do you notice that the object has a downward force mg? But do you see the object not moving downwards? Shouldn't the object fall downwards because there's a downward force mg? Do you notice it's maintaining a constant height, right? So can you tell me, vertically speaking, what is the object in? And like in terms of vertical forces, what is the net force? Object কিন্তু দেখো কোনো height change করতেছে না. Is the object going up? No. Is the object going down? No. So what can you say is the net vertical force acting on the system? Right, zero, right? It's there's no resultant force here. So we will try to exploit that idea. দেখো কেমনে করি এটা. It's a very interesting derivation, okay? So resolving vertically. So what does that mean? Or vertically forces guloke consideration nibo. Resolving vertically, the system is in equilibrium vertically, right? There's no net force because how do I know it's in equilibrium vertically? Because it's not going up or down. Isn't that what resultant force zero means, right? So system is in equilibrium vertically, which means the sum of forces upwards is equal to the sum of forces downwards. What's the force acting upwards? Because it's not magic, right? It's just basic physics forces. So there must be some solution for it. So there is a solution. There's an upward force here, right? T cos theta. And what's the downward force here? Mg. So using that, what did we establish? We figured out tension is mg divided by cos theta. Now you might be wondering, okay, but why did we go for this particular expression? Because we do not know what tension is. We want to know what tension is to find this force, right? আমাদের এটা দরকার at the end of the day, right? Our aim is to find this force. That's the centripetal force. So if I do not know what my tension is, I wouldn't be able to solve it, right? Do I know what M is? Yes. Do I know what G is? Yes. Do I know what theta is? Yes. So I know what these are, right? So I can find my tension. Let's keep it aside for a moment, okay? So now let's resolve horizontally. So resolving horizontally. So what do we get when we resolve this horizontally? Horizontally, interestingly, there is no equilibrium. There is actually a what force horizontally? A net force. Because there's a force this way, there's no force that way, right? So system is not in equilibrium, which is perfect for us because circular motion can never take place if the system is in equilibrium. Because there has to be a net force acting towards the center. I think the important, the F centripetal is a net force. So what do we write here? Resolving horizontally, F net is the centripetal force. Okay, so there is a net force towards the center, which is the centripetal force. This is very important that a system must have a net force to be applying circular motion. Because if this force and that force cancels out, then there is no force to take it inwards, right? So there has to be always a net force towards the center, which means Fc is equal to, right? Sorry, let me use the other color. Fc is equal to T sine theta, which is the force acting towards the center, which further means using this equation, right? We can replace the tension with this. So Fc is equal to mg by cos theta into sine theta, where sine and cos will give me tan. So therefore, we have this wonderful equation. Centripetal force is mg tan theta. That's the formula for my centripetal force. But we can make this even more interesting. How? Look at this. What's the formula for centripetal force? Mv squared by r or m omega squared r, right? So let's just use any one of them. So mv squared by r is equal to mg tan theta, right? See, I told you something earlier today that the masses cancel out. So this mass and that mass cancels out. And what is v squared by r? Acceleration, right? So what do we end up with? A equals to g tan theta. This A, by the way, is the centripetal acceleration. So what's the final line, bottom line to this? That when an object undergoes circular motion in a conical pendulum, right, this acceleration depends on this expression, and it doesn't depend on the mass that's here. So if I had like a 5,000 kilogram boulder here, right, hung from this rope, it will still go in the same circle because the mass doesn't really affect my circular motion. So what affects my circular motion? It is the angle. The angle is the important part of my circular motion, okay? So the angle is responsible for circular motion. So if I change my angle, I have variations in circular motion. So let me try to show you this. How can you show this? Just a moment. Angle, right? Angle there. Show the right second. No, ito angle na. I'll show you in a bit. So basically, you can change the angle, and the angle will cause the object to rotate at different rates. Okay, but before that, I think this is the one. All right, yeah, this is the one. So look at this. I can screen share is gone. I think just a moment. এই যে আমরা যদি এখানে দেখি আমার হচ্ছে আচ্ছা এটা view angle. Never mind. So if I run this, right, and I show the free body force diagrams, do you see that there's the t sine theta that we just derived acting towards the center of my circle, right? And if I vary the radius, right, see the question doesn't have anything to do with mass. The simulation has nothing to deal with the mass. It's the length and the radius and the angle that matters. See, I'm varying the angle. So because I'm varying the angle, the whole motion is changing. Okay, so let's just do a math and then try to understand what is this all about. Okay, so first of all, conical pendulum, these are the free body force diagram. This is the centripetal force. This is the expression for the centripetal force. This is the value of the centripetal acceleration. That's it, right? Now, what kind of questions do we get from it? Because it seems like this is it, right? Let me explain. What if, look at this carefully, what if I try to make it completely horizontal? Is that possible? So completely horizontal. Okay, let me get rid of this. If I see from the side, there's something very interesting happening here. Do you see I have increased my velocity to the maximum value? I have changed my rope to the maximum possible length, whatever maximum is possible. Do you guys notice that the rope is not horizontal? There's a small angle there at the top. Do you see it's not 90-degree between the rope and the like stand? Turns out it's mathematically, physically impossible for you to rotate a string horizontally. It is not possible. So you might try this, it won't work. তুমি যদি একটা rope নিয়ে you whirl it around horizontally, it is impossible that it will be completely flat. Okay, mathematically we can prove that it is not possible for it to be completely flat. You'll see reason behind it. Okay, so anyways, we'll look into that. What if the rope is vertical? Vertical possible. Vertical to vertical hobe. So vertical meaning like if you spin it in this manner, like a fan blade, it'll work. But horizontally, right? It's not possible. Look at your fan as well. You notice your fan blades are actually like this. They're tilted downwards. Check kore dekho, they're not flat. Though it is possible to make them slightly flat, but they will always be slightly tilted like that. And there's a good reason behind that, which we can come from here. So we'll come to that later on. So there's a question in your past paper when they talk about this merry-go-round or some ride in the theme park, and they say that it's impossible for someone to go like this. Why? You need to answer. Okay, so we'll come to that later on, but let me just give a small example so that I understand you have understood what I've explained so far today. So this is the example. It's based on the conical pendulum, nothing else. So what's the question? So you have a conical pendulum with mass of 400 grams, length of 1 meter, length of 2 meters, and what else do we have? The angle. That's the most important part that's been provided to you guys. So the angle subtended here is 30 degrees. Okay, so what do you need to find out? Quite straightforward, simple question. Find the number of revolutions per second for this Go ahead. Find, so I'm giving the equation there as well, like whatever you need. Find the number of revolutions per second for this conical pendulum. So I'm making this conical pendulum go in a circle. Just try to imagine you're making this go in a circle. At this particular angle, with this length of rope, with this mass, right? There's only one possible time period available. Find that. Do we need to convert the angle into radians? No, no, because if you want to use it here, no, you don't need to. You don't need to actually. None of these places, you can keep it in degrees in all these places. Not needed to convert into radians. So try to find out what's the value. This is revolutions per second, okay? Like frequency. All right, I'm seeing a common answer, which is 0.38. Wait, 0.38, right? So 0.38 is the most common answer. Let's see if that's the answer or not. So how do you solve this? First, we need to find out the centripetal force, right? So how do we find centripetal force? You could directly have used this equation. No problem in using it directly, and even in your exam. So the centripetal force is equal to mg tan theta, right? So what is centripetal force going to be? I'm going to find revolutions per second, right? So I'm going to use time period equation. So m omega square r equals to mg tan theta. That's what I'm going to use, and the mass cancels out. So you see the mass is not a factor here. Now, what's omega? We will find that later on, or we can break it down here as well. 2 pi by t whole square times radius is equal to g is 9.81 into tan 30. Keep it in degree mode. No need to convert this into your angle. However, what is the radius? This is where students make a mistake. If you took your radius as 2, that's wrong. Radius is of this circle here, right? So I'm going to a circular radius break. So the radius is not 2. So you have to use a bit of trigonometry to figure out the radius. How? This is a triangle, right? And this is your 30 degrees. And this is your 2 meters. So what is that radius there? So simple, sine equals to opposite by hypotenuse. So therefore, x equals to 1 meter. So the radius has to be 1 meter here. And from there, we're going to find out t. Can you find me what the value of t is by doing this math? Make sure you keep it in degree mode for the tan. What is the value of t here? There's a question, will this equation be given in the exam? So whenever this question came so far, they asked you to derive this first. So I did derive korte hoy. It won't be given in the exam. Okay, 2.64. Correct me if this is wrong. So 2.64 is a time period. But I want to find revolutions per second, which is what? Frequency, right? So therefore, frequency equals to 1 by time period. How much is that? 1 by 2.64. All right, 0.38 revolutions per second. And I'm quite glad and surprised at the same time. Almost everyone got this right. So that's really good. Tomra ki a radius 1 ne korcho naki 2 ne korcho? Obviously 1 ne korcho mone hocche, otherwise answer asaর kotha na. But yeah, very good. Okay. This is a 4-mark, 5-mark question in your syllabus. So if you have actually understood the process and got the answer, excellent. Okay. So that's very good. Yeah, so this is like a starter, obviously, when it comes to conical pendulum. We'll look into some subjective scenarios next class. Like, what if we start to spin it really, really fast? What happens? Or what if we, have different mass here? Or what if the length of the rope is increasing? Many variations, subjective questions. Okay, so we'll look into those, don't worry. So once we are done with that, our main agenda for next class is this one. This one is really, really important. The vertical circular motion. Quite challenging and important at the same time. Should it be 0.4 to least significant figure? Yeah, 0.4 is also possible because I've given everything to 1 significant figure. But generally in the exam, they give more stuff to 2 significant figures. So depends on that. You round it off accordingly. So there you go. The conical pendulum concept. Okay, so I think you guys understood. At least those who have answered, you are all right. A couple of you got it wrong. Asha kori you have realized your mistake. But this is it. This is the conical pendulum. Okay. Next class, we'll look into the subjective questions. How and why, the explanation part. But yeah, that is it. Jara Buchonai, just have a look again. I'll upload this obviously. So we will continue with this next class. Okay. So I'll see you guys then.